Hi everybody. Today we will be talking about three things. The first thing is percent composition. Percent composition basically describes the percent by mass of each element in a compound. So for example, if I had nitrogen monoxide, how would we find the percent composition? Well, we know from our previous videos that nitrogen has a smaller average atomic mass than oxygen. So as a result, nitrogen will make up a smaller portion of the total mass, while oxygen will make up a larger portion of the total mass. Now let's prove that for ourselves by doing some math. So nitrogen has an average atomic mass of about 14.01, while oxygen has, 16.00. So let's use those numbers to help us calculate the mass percent of each of these elements. So this is 14.01 AMU, and this is 16.00 AMU. Then don't you agree that the total average atomic mass of nitrogen monoxide is 30.01 atomic mass units? Well, since we know that, we can do mass percent, because percent by mass just means the mass of each element divided by the total mass. So little m is, something like the mass of the nitrogens, and the total mass is just that. And remember to multiply by 100% because it is a percentage. So let me undo all that, and let's try to find the percent by mass of each element. So for this element, nitrogen will be 14.01 AMU over the total, which is 30.01 AMU, and then you multiply that by 100%. So doing the math, I get 46.68%. Now let's try that for oxygen. So oxygen is 16.00 over 30.01. And notice how I don't include the units, because I know that the units will cancel out if you have the same units on the top and the bottom. So we do the 16 divided by 30.01, and you multiply by 100%, and then we get a number which is 53.32%. So from these calculations, we can conclude that in nitrogen monoxide, 46.68% of its mass is made up of nitrogen, and 53.32% of the mass of the molecule is made up of oxygen. So remember, this is based on the average atomic mass, meaning that on average in nature, if you take a nitrogen monoxide molecule, it will have a percent composition of this and this. But if you look at each individual nitrogen monoxide molecule, then you'll see that it is not exactly this or this. These numbers are just averages, because remember, the average atomic mass is taking the average of all the isotopes of an element and taking the weighted average of it. So this is not an exact percentage for each and every single individual, molecule of NO. This is just a description of, overall, if you have a sample of nitrogen monoxide, on average, 46.68% of its mass will be made of nitrogen. So scientists tend not to study just one molecule. They tend to study a large sample of molecules. For example, this bottle might have maybe a mole of nitrogen monoxide, so that's a lot of this stuff, and that's why it's more appropriate to be using average atomic masses rather than the atomic masses of nitrogen 15, because we know that not all nitrogen is nitrogen 15. It could be nitrogen 14 or any other isotope. So that's why using the average atomic mass is appropriate in most cases. Let's do one more problem involving percent composition. Let's look at a salt. We will look at sodium chlorate. Now, we know that sodium chlorate is made up of a sodium cation and a chlorate anion. So how can we find the atomic masses, or the average atomic masses, of ions? Well, to tell you the truth, an ion is just a molecule or a compound that has lost or gained an electron. And since the mass of an electron is so small, we usually ignore the fact that something has gained or lost an electron in our calculations. So as a result, if we want to find the average atomic mass of something like, a sodium cation, that will be generally just equal to the average atomic mass of just a sodium atom. So when dealing with ions, we usually just stick to their average atomic masses as listed on the periodic table, despite the fact that it has lost or gained an electron. So let's find the percent composition. So we know that sodium from the table is 22.99. We know that chlorine is 35.45. And we know that N-oxygen is just 16.00. But since there are 3 of them, we have to multiply this by 3. So let's just erase this, and we know that 16.00 times 3 is 48.00. So this is our total mass. So when we add this all up, we get 106.44 atomic mass units. So let's now find the mass percentages. So 22.99 over 106.44 times 100% is equal to approximately, 21.60% sodium. Now let's do it for chlorine. Chlorine is 35.45 all over the total mass, which is 106.44, times 100%, and we get around 33.31% chlorine by mass. Now let's do the oxygen. That will be just 48.00 over 106.44 times 100%. And if you do the math, it comes out to be 45.10% oxygen. So notice how these 3 mass percentages add up to a number that is very close to 100%. And the only reason why these don't add up to 100% exactly is because along the way we rounded off, and as a result we have a number that's slightly above 100%. But as long as it is very close to 100%, then we should be fine. So in sodium chlorate, 45.10% of the mass will be oxygen, 33.31% of the mass will be chlorine, and 21.60% of the mass will be sodium. And remember that when we calculated the molar mass of a compound, we could either use the average atomic mass of the individual elements, or we could use the molar mass of the individual elements. So the same applies for here. We could also use molar masses in order to get to the same conclusion. So the math would all be the same, but it would look slightly different in terms of the units. So if I wanted to calculate the mass composition of sodium chlorate and use molar mass, well, we know that 1 mole of sodium chlorate contains 1 mole of sodium, 1 mole of chlorine, and 3 moles of oxygen. So let's calculate the mass of sodium chlorate in a mole of sodium chlorate. So we know that 1 mole of sodium is 22.99 grams. We know that 1 mole of chlorine is 35.45 grams. And we know that 3 moles of oxygen weighs 48.00 grams. So if we add all this up, we will get the mass in 1 mole of sodium chlorate. also known as the molar mass of sodium chlorate. So the math is the same for the other one. So our molar mass would just be 106.44 grams per mole. And in order to find the mass composition, we simply just take the molar mass, or actually, to be more accurate, the mass of each element in the compound, and we divide it all by the total mass of the compound, assuming that there is 1 mole in total of the compound. So in this case, we have 1 mole of sodium chlorate, and the top would just be any element. So for example, if we wanted to look at oxygen, we know that in 1 mole of sodium chlorate, it weighs 106.44 grams in total, and we know that the oxygen weighs 48.00 grams, and then you kind of just multiply by 100%, and you get the same exact percentages for here as you did for here. So the math is all the same. You could choose to either use atomic mass units or the molar masses. The choice is up to you, but let's move on now. So now let's talk about what the difference between an empirical formula and a molecular formula is. An empirical formula is the simplest ratio of atoms written in a chemical formula, while in a molecular formula, all atoms are shown in an unsimplified ratio. So for example, if we take the molecular formula N2O4, which is dinitrogen tetraoxide, then the empirical formula would just be the simplest ratio of the atoms. So the unsimplified ratio is our molecular formula, and our empirical formula is the simplest ratio. So how do we simplify the ratio of 2 to 4? Well, you just divide both sides by 2, and you get NO2 as our empirical formula. Now let's find the empirical formula for methane, CH4. Methane is our molecular formula because it shows all the atoms in methane, and we know that methane is CH4. So how can we simplify this to an empirical formula? Well, the truth is, the empirical formula for methane is the same as its molecular formula, since you can't simplify this any further. And keep a note that these ratios are whole numbers. So your ratios have to have whole numbers in them. So you can't just have, C0.5 and H2. You absolutely cannot do this. You can only have whole number ratios between atoms. So now that we learned what empirical formulas and molecular formulas are, let's try to get an empirical formula given the percent mass. Now this is just the reverse of finding the percent masses from the molecular formula, such as this one or this one. Oh, that's the same thing, sorry. Or this one. So in these examples, we went from the molecular formula to the percent masses, but this time we will go from the percent masses to the empirical formula and then to the molecular formula. Now, why do we need this extra step to get to here? Well, to tell you the truth, the empirical formula has the same mass percentages as the molecular formula, and let me give you an example. So for example, if we wanted to find the mass percentages for N2O4, they would be exactly the same as the mass percentages for NO2. And the reason for this is because NO2 is just N2O4, but divided by 2 for each atom. And even though the number of atoms have decreased, the ratio between atoms stay the same. And because the ratios of the atoms stay the same, the mass percentages of each atom of the compound also stays the same. So this is 1 to 2, this is 2 to 4, but if you simplify it, it's 1 to 2. So that's why when we're given mass percentages, we will only be able to convert it to the empirical formula first, and we need a bit of extra information to get to the molecular formula, which I will talk about very soon. So let's do a practice problem. what is the empirical formula if 40% of the compound by mass is carbon and 53.28% of the compound is made up of oxygen, and the compound is composed of carbon, oxygen, and hydrogen? Well, we first notice something very odd. The mass percentages don't add up to 100, and they're supposed to. So why is that? Well, we're missing the mass percentage for hydrogen, so that's why it's not adding up to 100, because if you add up all the masses of the elements of a compound, you will get 100%. So how do we find the mass percentage of hydrogen? Well, the simple answer is you just subtract. So we know that the total mass percentage is 100%, and this is equal to the mass percentages of the individual elements. So it would be 40.00, that would be from the carbon, plus 53.28, that would be from the oxygen. So let me put the percentage signs just in case. And then the percent H will be our variable. So if you do the math and you take out a calculator and you add these two up and subtract it from 100, you will get that the mass percentage of hydrogen will be 6.72%. So I kept sig figs in mind. So this is the mass percentage of hydrogen once you do the math. So now that we know that the mass percentage of hydrogen is 6.72, let's erase all of this and write that down, actually. So 6.72 will be the mass percentage in the compound. So H is 6.72%. So now that we have the three mass percentages, let me show you a trick in order to get the empirical formula. If we assume that this compound is 100 grams, then we can find the masses of the carbon, the oxygen, and the hydrogen. So if the compound is 100 grams and 40% of it is carbon, then we will know that the mass of carbon will be 40.00 grams. And note how I'm still staying true to significant figures, because when I assume 100 grams, I mean exactly 100 grams. So the only thing that would be uncertain, or aka the things that have sig figs, would be the mass percentages. So this is an exact number in our case because we are assuming that it's 100 grams exactly. So it would be 40 grams carbon, 53.28 grams of oxygen, and 6.72 grams of hydrogen. And now that we have the masses of the C, H, and O, we have to now convert these grams to moles in order to put the moles in, ratios. So let's now do that. So let me pull up a new table and write the masses down. So 40.00 grams of carbon, 53.28 grams of oxygen, and last but not least, 6.72 grams of hydrogen. And note how the masses are equivalent to the percentages. So now that we have this, let's convert everything to moles. And the reason why we're doing this is because the molecular formula, or the empirical formula, or any chemical formula, will have a ratio of atoms, and since moles are just a bunch of atoms, or 6.022 times 10 to the 23rd atoms, then a mole is basically just a scaled up version of the atom. So by finding the ratios between the moles, we are essentially finding the ratios between the atoms, since moles is just a scaled up version of atoms by a factor of, 6.022 times 10 to the 23rd. So now let's actually get to the math. So 40.00 grams of carbon needs to be converted into moles of carbon, and in order to do that, we simply just multiply by the conversion factor, which is the molar mass. So we know that carbon is 12.01 grams per mole. So note that how the grams will cancel out, and you're left with, well, according to my calculator, you get about 3.331 moles of carbon. Let's do that for oxygen. So we're going to multiply by the molar mass in a way that cancels out the grams. So in this case, the 16.00 grams would be on the bottom. So 53.28 grams times moles over 16.00 grams will give us 3.330 moles of oxygen. And we do that for hydrogen, so I'm not going to say it aloud. I will let you do the math yourself, and you will get 6.653 moles of hydrogen. Now, in order to simplify this ratio, we have to divide by the smallest number. So in this case, our smallest number is 3.330. So let's just divide all the moles by, 3.330 in order to get our simplified ratio. So if we divide 3.330 by 3.330, we get 10. We get, this is just about 1C, and this is 2H. So the reason why I ignore sig figs is because the ratio between atoms are whole numbers. So therefore, I don't have to worry about sig figs because I know my answer will just have one whole number. So we know that the ratio between CO and H is 1, 1, and 2. So let's now write the formula. So in order to write this, our empirical formula will be CH2O. And remember how I said that the H always comes before the O and the N? Well, in this case, it does that. So CH2O is our empirical formula. So how do we find the molecular formula? Well, in order to find the molecular formula, I have to give you the molar mass of our compound. If I told you that the molar mass of the compound is equal to 180.16 grams per mole, then you would be able to figure out the molecular formula. So we know that the empirical formula is CH2O, and we know that our molecular formula will just be a scaled up version of it by a factor. So in order to figure this out, we have to find the molar mass of the empirical formula. In this case, the molar mass of our empirical formula will just be 12.01 grams per mole of carbon plus, 2 times 1.01 grams per mole of hydrogen plus 16.00 grams per mole of oxygen. And we get that the molar mass of CH2O will actually just be 30.03 grams per mole. So now we just simply have to figure out how many times more is this than this? Or in other words, what do we have to multiply 30.03 by to get this number? Well, we could just divide 180.16 over 30.03 in order to get our scale factor. So this is approximately equal to 6. And remember, no sig figs because these are all atoms, and atoms are always whole numbers, so we don't have to worry about that much. So this is going to be times 6, and as a result, our molecular formula will actually be C6H12O6. And incidentally, this is the molecular formula for sugar. Or to be more specific, glucose. So what if you were making a table like this one, and you have these three numbers and you divide it by the smallest number, and you got numbers that were not whole ratios. So for example, here we got 1 to 1 to 2, but sometimes that doesn't happen. Sometimes you get 1.5 to 2 to 1. So these are not whole number ratios. So how would you find the empirical formula then? Would you just write C1.5H2N? Well, no, you wouldn't. You want whole number ratios for your, your molecular formula or your empirical formula. So you have to make it so that happens. So we could scale things up. We could multiply everything by 2. And we know that 1.5 times 2 is 3, 2 times 2 is 4, and 1 times 2 is 2. So our true empirical formula would be C3H4N2. Now let's try this one. What if I got the ratio 1 to 1.2 after dividing by the smallest number. So usually in previous problems, we've divided by the smallest number and got whole numbers. But what if we instead got decimal numbers such as this one? Well, we would try to make it so that it would be whole numbers by scaling it up. So 1.2 times what will give us the smallest whole number? And the answer to that is 5. And this would be 5 as well. So we would have a 5 to 6 ratio. Now you might be wondering, how did I figure out it was 5? Well, I know that 0.2 times 5 will give me 1. So therefore, if I multiplied 1.2 times 5, it would give me a whole number. So 1.2 times 5 is 6, and 1 times 5 is 5. So therefore, our empirical formula would be C5H6. So sometimes empirical formulas don't have the number 1 in them, and that's perfectly fine. Sometimes you just have to scale them up. And in the next video, I will be doing some challenge problems involving molecular and empirical formulas. So stay tuned and have a wonderful day.